All right, got a few questions asked by email. The first is regarding some questions in the packet for Organic 1. So let me bring that up on my screen. So, quick question regarding the reagents for primary alcohol substitution. When should I use CCl? When should I use SOCl2? Thanks. So, with a lot of organic problems, there are actually multiple solutions to these types of problems. The choice of solution depends more on the situations you're dealing with, and in practice, you would be more kind of looking at the lab you're working in. So, based on what resources they had, that would dictate basically what you would use. So the big thing we're trying to squeeze out here is that identifying, particularly at this point, Sn1, Sn2, E1, E2 pathways. So you can see there is a lot with this problem. Almost done writing up all the things. Right, so these are boxed. These are boxed. These two are boxed. 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 And boxed. Almost done. OH. We have to make sure OH is. And down here we've got bromides. Here we have a single bromide with inversion. And here we've got just the alkanes. Alright, so with these, you're just substituting the Cl with the OH. Here you have one product that's stereospecific. Here you have two products. This is not stereospecific. So this is implying an Sn2 versus an Sn1 pathway to make this go. The Sn2 is going to give you a racemic mixture of both the R and the S compounds. Here we're sitting on a tertiary carbon, so we're not going to get carbocation rearrangement. But here we definitely have total inversion. So to do the Sn2 pathway, we need an OH source. In this case, it's going to be a sodium hydroxide, and we need a non-protic, low dielectric constant solvent to drive this type of reaction. So we're probably looking at something like tetrahydrofuran. Probably couldn't do this in something like hexanes, but a very low polarity solvent that pretty much makes sure that we don't end up generating a carbocation. So for this pathway, we just need to pick a solvent system that makes sense in terms of replacing the chlorine with an OH that isn't going to promote a carbocation pathway. For this one, we can work with something like sodium hydroxide and water. Water here is a nice high K dielectric constant solvent. It's going to stabilize the carbocation intermediate. Chloride here should be a decent-ish enough leaving group that will end up topping it off with a plus and getting our OHs in there. Now, down here with the stereoselective, again, you see 2 and 1. We get two products with an E1 or with an Sn1 pathway versus an Sn2 pathway, which would guarantee us stereoselectivity. Now with this, the easiest way to do it is PBr3. So PBr3 here is going to give us a single step where we can convert this hydroxide stereoselectively into the other RS stereoisomer. Another option, if you are so inclined, you can use tolusyl chloride in sodium bromide. Honestly, tolusyl chloride here is not water stable, neither is PBr3. So if you got to deal with a water unstable compound and you have to run this effectively air free, you're better to kind of do it in a single step, which is where your PBr3 is going to come in. Now I got a question got asked, when would you use tolusyl chloride over SOCl2? Tolusyl chloride is used for selectively removing OH groups, making them good leaving groups. And thionyl chloride is a way of also stereoselectively converting an OH group to a chlorine. So if you're trying to do nucleophilic substitution and you want to pick off the alcohol and guarantee an Sn2 pathway, that's when you would use tolusyl chloride. You would use SOCl2 if you're trying to stereoselectively convert an alcohol directly to a chloride. You could do that with tolusyl chloride. You could use TSCl and then follow that with like sodium chloride. But Again, it's going to depend on the availabilities and the types of synthesis you're doing. Both tosyl chloride and SOCl2 are not very air stable, not very water stable. So they're both going to require to kind of you run this under air-free, water-free conditions. So again, there's multiple answers to this. Again, you could do tosyl chloride and sodium bromide. If we were trying to make this chlorine, you could do tosyl chloride and sodium chloride. I would just say the PBr3 is the easier step. For substituting this, NaBr, and probably in water, just to kind of drive it off. You are going to struggle with have issues of selectivity, so maybe not water. Trying to think of a good, methanol, NaOH. So basically a polar solvent that will allow you to dissolve the sodium bromide. And again, what we're trying to do here is we're trying to promote the water. Honestly, a little acid would probably go a long way too, making this reaction get a little better, to give you the OH2 plus to pop off and let the bromide attack. Now over here, this is a straight elimination mechanism. H2SO4 will actually work for both of these. You can work with something like tert butoxide, but you will get competing reactions where tert butoxide will deprotonate the alcohols. So particularly if you have an alcohol, and here it doesn't matter if you do E1 or E2, it's going to give you the same outcome. I would definitely say with water, sulfuric acid would be the better drying agent. Now the second question, 2, 4, 6, 7. And we want to know the first reagent to get us towards this compound here. Oops. And what you'll notice here is that it's missing the stereochemistry. There's a big reason for this. One, we're eliminating it so we don't care. And two, it's kind of to tip you off to the mechanism. Easiest way to do this in terms of hypothetical chemistry, Cl2 light, monochlorination is going to favor tertiary carbon substitution. Now, this OH does sit on a tertiary carbon. That said, the oxygen spilling electron density off, so you're probably still going to be pretty selective for getting there, but you could definitely get some products where this is here. Next thing it tells you is to add sodium. What sodium does is deprotonates that alcohol. And this is going to end up becoming a really good nucleophile. So what it's going to do is it's going to attack this chlorine, bump it off, and what we'll end up with, if we count them, 1, 2, 3, 4, 5, 6, 1, 2, 5, 6. And then we'll also have a propyl group hanging off. So this is just nucleophilic substitution. In this case, is going to be an Sn2 pathway. The Sn2 pathway here is going to attack the chlorine. Now, you could get some elimination where it pulls the hydrogen off and you end up getting something like this. But the predominant product here is going to be the substitution where the chlorine gets removed and we end up generating this bicyclic complex. So that was 251, 252. Bring up the packets. First and third on page 9. So again, for the first and third mechanisms, I talked about this in the Tuesday live stream, so I go back and recommend looking at those for the first and third. The first is just Friedel-Crafts acylation. That's covered in the test one materials, so you need to go back to the test one material and look at that. And then, wait, did I already answer this question? page 9. Let me make sure I'm on the right page. Yep, this page 9. First and third, I've already answered. So I would go back to the Tuesday live streams and look at that. Big thing you're doing with those, first one is Friedel-Crafts acylation, so that's just test one material. Second one, you're using a Jones reagents to create a dicarboxylic acid, and then you're using heat or a strong drying agent like sulfuric acid to remove the water to give you the acetic anhydride. Mechanisms, page 11, 12, 13, 14. Again, I covered this in the live stream Tuesday, so I answered these questions about these molecules, so I would encourage you to go back to the Tuesday live stream and look those up. Definitely went through page 11, went through page 12, went through page 13, and went through page 14 as well. All these involve protecting groups. You start with by adding the ethylene glycol, so particularly with the fourth one. If you try to hydrogenate this straight, you will end up hydrogenating the ketone as well, and you'll end up producing the alcohol. Now you could back convert this using an oxidizing agent. That said, you can just work with ethylene glycol as your protecting group. Hydrogenate that. And then take that off with an acid, and that'll get you back to the desired ketone. But again, pages 11, 12, and 13, I answered those Tuesday, so I'd recommend you go back and look at the live stream from that day where I go over how to work these out. Page 15 and 16 in reaction, why are there no reaction? The first count page, there's typo in the NH2. So as I mentioned in the Tuesday live stream, this has to do with stabilities of the molecules. So for the molecules, acyl chlorides are the least stable, carboxylic acids are the most stable, and there is a pattern of stability between those. That's actually in the notes, so I would recommend you go to the PowerPoints, open those up, and it actually gives you a list of all the different ones. We're going to kind of stick away from the thiol compounds, but again, that's in the notes. I would recommend you go look at it, look for it there. That's why there's no reaction. So some of these, the amides, which are the nitrogen in the NH2s, these are the second most stable. So you can't form an ester from these. You can't form an acetic anhydride for these. So this isn't going to react with with ethanol, because that would produce an ester, which is less stable than the starting imide. Same thing's true of the thiol. You won't react with this because you would end up generating a less stable compound. So the driving force here is basically acid-base chemistry. Third column, NH2. Let me look up the key for that one. I'm assuming you're referring to the key. Nope, there's no typo in that one. You would end up producing because you have an hydroxide, you should finish up with something with a negative charge, and that'll give you the carboxylate ion. Can you explain the mechanisms of the compounds in pages 19, 20, 21, 22, and 23? So 19 I did in the Tuesday live stream. 20 I did in the Tuesday live stream. 21 I did in the Tuesday live stream. 22 I did in the Tuesday live stream. And I think 23 is the only one I haven't done. So for those pages, I would recommend you go back and actually look at those. Look at the live stream. That's got all your questions answered in it. For this one, we start with the benzoic acid. Actually, I answered this one too. So for this one, it's an HCl addition. This is a Friedel-Crafts alkylation. So you add first. You have to protect that ketone. If you try to add the HCl, it will react with the ketone to give you an alcohol adjacent to a chloride. So you have to protect the ketone, add the HCl, do your Friedel-Crafts acylation, and then you will remove the protecting group. Reactivity compounds. Again, those are in the notes. I would recommend you go look at the notes. It will give you a complete list of the reactivity series. So again, so the student that just emailed these questions, these were all answered in the Tuesday live stream. So I would recommend you go back to that video and look through it. Every single one of these has been worked out for you. All right, that's it for questions I've been emailed. I'm not seeing anything in the chat, so I'm just going to turn off the video. Again, if you have questions, please ask them in the chat. And here, these are not lessons, these are not lectures, these are office hours. So please, if you've got questions, just post them. The question got asked, we had to worry about pages 24 through 30 on the packets. This is for organic too. You're not going to see problems like this. They're going to be a lot more straightforward. This is more kind of getting you to understand things outside of a context. So major issue students typically have, particularly when they take courses, they kind of get tunnel vision with a lot of this. So if it's not presented as this goes to this, they can't really apply what's been learned. So the point of those last pages is to kind of like pull you out of a context of here's A plus B, what does it go to, and more getting you to focus on the bigger picture. So if you were to do this practically, what would it look like? How would you apply all the things you've learned to kind of grow towards a more process-based approach? So with exams, typically the exams focus a lot more on individual assessments. That's just for practical reasons. We're assessing individual ideas, so the problems tend to be a lot simpler. But I'm not going to say like, oh, you don't need to worry about it. You need to be able to answer those types of questions because you're not necessarily going to I can assess a concept multiple ways, and the point of those last few pages is trying to get you out of the mindset of approaching these concepts all from the exact same way and trying to identify when the concepts are being applied. So something like go So something like page 26, when you're processing the ethylene and you've got the potassium permanganate, and you know potassium permanganate should generate two things. It should either generate the diol or it should generate aldehydes or ketones. And that's what be coming out of reactor stream 3 and 4. That's kind of the idea, is that it's asking you a very simple question: what does an alkene do in the presence of potassium permanganate? And there's two options: you can form the aldehyde ketone or you can form the diol. But it's not asking you it in that very black and white sense anymore. It's asking you in more of a, I'm not going to say obtuse or abstract because it's not putting it fairly, more of a context, more of a different context. It's still asking you the question, it's just not asking you it the same way. So I would say definitely go through those pages and work them out. That should definitely give you a lot more flexibility in terms of seeing the concepts and learning to identify how to apply the concepts you learn, because you're given a problem and now you kind of have to go through the different concepts you learned and figure out how they would be applied to this situation. And it should make you a bit more adaptable, particularly if you look at the synthesis of problems that appear on the exams. The synthesis of problems on the exams, they don't tell you what to do. They just say, here's one thing, make another. And if you're trying to memorize like problems out of the packets, you're never going to see those. But what you will see are different concepts being applied. And so by practicing these types of problems, you get a bit more versatile in terms of identifying which concept is probably the relevant one or which concept is being assessed. And it just kind of makes your life a little bit easier when you start dealing with the much higher end problems. So again, you're not going to be assessed this way, but this is definitely very helpful in terms of building up your ability to identify the concepts that are being assessed and figuring out when to apply them. Right, gotta ask, with a given compound, if there's a hydrogen on both the nitrogen and adjacent carbon, which H would prefer to get removed if both have hydrogens that are available? Generally speaking, the hydrogen is probably going to come off the nitrogen. The nitrogen has a lot more acidity associated with its hydrogens than the carbon, so the CH bond is stronger than the NH bond. So if you have to make a choice between pulling a hydrogen off a nitrogen versus pulling a hydrogen off a carbon, you're definitely going to go to the nitrogen first. And then if you got bonds left over, then you'll start pulling it off the carbon. So I guess you're asking more if you had a situation like this. We'll just put an R here versus a C, H, R, and R. If you're going to start basically doing this elimination to get the OH off, which comes off first, and again, I would definitely say the nitrogen's going to lose it first. These hydrogens are a lot more acidic. So you lose the hydrogen, that comes up. Like I'm missing something. I am missing something. Missing another bond out there. So we'll lose the hydrogen, we'll form a bond. That'll pop the OH group off. I think that's going to be a lot more likely to occur than losing this hydrogen and getting that. And even then, you're probably going to get some degree of tautomerization there anyway. But definitely, in terms of a final product, hydrogen's coming off nitrogen first just because they have weaker bonds. All right, so that's it for office hours. If you got questions, please feel free to email in advance, and I will see some of y'all tomorrow.